Morning, everyone. I'm just pulling out the final exam whose link I'd given you on my courses. How's everybody doing? If you have a look at the final exam schedule, something which I had not done before I sent the email, and so that's completely my fault. But have a look at the final exam schedule. It's completely spelled out. Opening date, closing date, everything is there. I haven't decided anything yet. Look, you should expect some questions with variables like on the midterm, for sure. There's going to be some of that. But you should also expect other kinds of questions as well. Jacob, there are no mistakes on web work. Let's say that. So whatever it is, either if the answer really is infinity, there should be a way to input infinity. If you're inputting infinity and it's telling you it's incorrect, well, let's just say that. Just read the question in complete detail. If they're telling you how to input infinity and then the web work is not accepting it, that's because that's not the answer. We do have class next week, Monday and Wednesday. Wednesday will be our last class. Will there be a lot of proofs? Not a lot. You could expect some. And again, it depends what you mean by proof. If there's a question that asks you to show something, I feel there will be no new material. We have finished with the material. We've been doing revision for the past few days already, and that's all we're going to do. Annie, I want to say we did that question before. I think we did that question on Monday. We did that question on Monday with R and H in general. How are we doing? Questions on stuff we want to do? Or are we going straight into the 2004 final? Go ahead, Georgia. Good morning, everyone. Come on in. Georgia is going to give us a graphing question. Are you giving us a graphing? Here we go. Did we not do that question as well? I want to say we did that question in class. Am I wrong here? No, I'm pretty sure we did that question in class already. Can anybody confirm? Anyone? That question seems, no, really? That question seems oddly familiar. Perhaps we had only, all right. Well, maybe it was in office hours then. All right, let's not, let's do it then. Let's do it. Or maybe the question was just a, wait, we did? We did it, yeah, there it is. On November 13th. All right. Are there any questions? Or let's move on to the past final then? Anything you want me to cover? No? Let's go with the past final. We were looking at question 2, which asks to find the derivative of x squared plus 3x over x. And again, this is almost embarrassing as a question on the final, right? The derivative, of course, is easily seen to be 1. As long as x is not 0. Yeah, so on Minerva, Minerva says Thursday is our last class. And Thursday, so what Thursday actually is first of all, it's a day that follows a Monday schedule. And it follows a Monday schedule, and it's a day that is meant to replace Labor Day Monday. Yeah, so I mean, it's a day that's there. If we need it, we certainly don't need it. So we will not have class on that day. I mean, of course, on an exam, you need to write. You don't need to write down which rule you're using. But the point is here, you don't need to use the quotient rule. We can simply rewrite this as x squared over x plus 3x over x, which is just x plus 3. And the derivative of x plus 3 is, of course, 1. Wednesday is our last class. Wednesday of next week. So we have 2 more days, and that's it. I mean, in general, some people will have, some classes will use that extra day on Thursday. We will not. I am teaching math well, let's say I am scheduled to teach math 141 next semester. Yes. Let me change the next one to x's. It says t's, but I'm afraid my t's look very much like pluses. Yeah, exactly. This question is trivial. I certainly don't expect anything like this on the final exam. This, you can expect something like this, but not that. Here, I mean, first of all, it was the first question in a series of derivatives, so maybe a confidence builder. Moreover, the trap was perhaps to apply the quotient rule without thinking. Nothing wrong with that. You'll get the right answer, but I mean, there's just room for error there. Do you have to include the x can't equal 0? Well, you probably should, right? Because you're canceling an x over x business, right? I mean, in the x plus 3 here, this function is differentiable everywhere, but this one is not. This one here, 0 is not in the domain. So you probably should. And you know, maybe that's what they had in mind here, to see if people would distinguish between x not equal to 0 and everywhere else. Who knows? Consider this. We're looking for the derivative. You know what to do. How are we going to tackle this question? Exactly. Thank you, Kamal. We're going to start. We're going to let y be x to the minus 3x, and we want dy dx. So we're going to take a ln to allow us to bring the power down. And then we're going to differentiate both sides with respect to x. What are we saying? We're saying ln x is minus 3x ln x. And now differentiate both sides with respect to x, assuming y is a function of x. Derivative of the left-hand side, 1 over y, dy dx, right? Implicit differentiation. Derivative of this is the product rule. So we'll differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one. And consequently, so dy dx is y times minus 3 ln x minus 3, and y was x to the minus 3x to begin with. There it is. Perhaps some of you may be wondering, here we did cancel out an x over x. And contrary to the previous question, we did not mention x was not equal to 0. Should we be doing that? Do we need to do that? Michael is asking if it's wrong to differentiate x to the minus 3x and get what he wrote down. Indeed it is. Right? We did not mention x was not equal to 0 there. The original, Celine is suggesting the original function has domain negative infinity to infinity. I don't think it does though. I think there's an issue if x is negative, right? If x was negative 1/2, then it would be negative 1/2 to the negative 3/2. You would be taking a square root of a negative number. My point was that this x over x that you're canceling, here you're assuming x cannot be 0, but we didn't mention it, but it's kind of incorporated into the ln x anyways, right? Because of the ln, x cannot be 0 anyways. So it's already kind of built in, if you will. But originally this, certainly, right, even at 0, this isn't defined because you have 0 to the power 0. You could take a limit to understand the behavior, but as it stands, it's not defined at 0 as well. So in fact, this is only defined for values bigger than 0. I don't know when Sean's review is. I'm sure he's working on it as we speak. Let's go back to Michael's suggestion though. Right, and Michael was treating x to the minus 3x, and he differentiated that by bringing the power down. I think there might have been a slight mistake there. And then subtracting 1 from the power. But this is treating this function as an exponential, as a power of x, right? It's x to the power something. But this is not a real number. This is a function of x as well. These are not equal. Logarithmic differentiation is the way to go here. Questions? What if you include the derivative of the inside? So times the 3, still not, I mean, you're below, yeah, no. Can't we just use the rule a to the x? So the derivative of this would have been a to the x ln a, or ln x, times the derivative of the inside, but it's not that either. Right? That means that a is a constant, exactly. But as I suggested in class when we were doing these kinds of questions, notice that the answer is actually the sum of those two. So it's treating this as both a to the x and x to the n. Isn't that Beautiful. Right? Consider this. Exactly, the 1 over y, you just bring it over to the other side, right? On the left-hand side, you have ln y, whose derivative is 1 over y times the derivative of the inside, dy dx. And then you just bring the y to the other side, and y, in this case, was x e to the minus 3x to begin with. We're looking for the derivative with respect to s. Whether it's s or t or x, it doesn't matter, right? Andre is asking about the alternate grading scheme. If you do better on the final than you did on the midterm, the final will be worth 70%. The other 30 coming from the web work. If your midterm mark was higher, then it will be 30% midterm, 30% web work, 40% final. We will calculate both marks and attribute the highest one. No need to sign up for anything. Derivative of tangent, you know what it is. Secant squared times the derivative of the inside, chain rule, right? What's inside? Inside is an exponential, whose derivative is the exponential, times the derivative of the inside. Inside is 2s, whose derivative is 2. Minus, what do we have here? An exponential, whose derivative is the exponential. 10s, yes. Times the derivative of the inside. Inside is 2 tangent, whose derivative is 2 secant squared. There it is. This doesn't really simplify much, so it's probably best to leave it as is. So Effie is asking why we use implicit differentiation on the last question and not this one. We don't have a formula for the derivative of something like this, right? In general, the derivative of a function of x to a power, which is another function of x. We don't have a formula for that, and there's no need for a formula. You can just do logarithmic differentiation by taking the ln. This allows you to bring the power down, and there's no issue there. Here, however, you know the derivative of each of these pieces. So there's no need to take the logarithm of both sides. For the final, we won't have to simplify unless specified, right? Let's do it the opposite. Simplify completely unless specifically told that you don't need to. Right, so if questions like these come up, we'll usually say don't simplify because it's easier to see if a mistake has been made or not. So simplify completely unless otherwise specified. All right, consider this. Well, I mean, I'll make sure to include it on the file. What do we have here? We have something squared. the derivative of which is 2 times that something times the derivative of the inside. What's inside? Hyperbolic cos, whose derivative is hyperbolic sine, times the derivative of the inside. What's inside? 3y, whose derivative is 3. If we wanted to simplify as much as possible, 6 hyperbolic cosine, hyperbolic sine. Question is asking us to find an equation of the line through -2, 0, which is tangent to y equals x squared and not horizontal. Let's take a moment to graph this to understand what really is going on, right? You have this y equals x squared. You know what that looks like, parabola. You have this point, -2, 0, which is not on the graph. And we're looking for a line that is tangent to this, but not horizontal, right? I mean, because of course, when x is 0, the tangent line to this is a horizontal line, which does go through this point. So that's not what they wanted. Is this the hardest final that was available? Well, here's the thing. You're doing this out of context with a book and this and that. It seems very easy, but people who wrote this exam was written by, I think, Professor Brown. Yeah, Professor Brown, notorious for giving hard exams. So if you think this is trivial, and you're right, it is, I'm sure you would have done very well on an in-person final exam. Could the tangent line be vertical? Well, you know that's not going to happen, right? Because this doesn't have any vertical tangent lines, right? So they don't want this tangent line. So what they want is some tangent line somewhere maybe around here, which goes something like this. Special indeed. All right. Well, I mean, you don't even have to draw anything. It's not necessary. But this is just to give you a flavor of what's happening. Well, tangent line at infinity, but infinity is not a real point. And let's not worry about that. Why wouldn't it point up and left? It could actually be somewhere here, right? It could be there. I don't know. And maybe there are 2 points. This will come out in our calculation. So we're not assuming anything. I'm not assuming that there's only one. There could be 2. And I'm not assuming it's here. It could be there. There might actually not even be any. I wouldn't expect there not to, but who knows? Let's see what happens. So what do we want? So fix a point. Fix a point, x equals a. This is where our tangent line will go through the point minus 2, 2. If x is a, y is a squared, right? The point on your graph, a squared. And the tangent line at this point has slope the derivative. Now you know the derivative. Let's say that. So if we let, I'm introducing an f of x that wasn't even defined before, then the slope m has derivative this. The derivative of that is 2x. So the derivative is 2a. So your tangent line y equals 2ax plus b, and it has to go through this point. So a squared is 2a times a plus b. So a squared is 2a squared. So b is minus a squared. So your tangent line has the form 2ax minus a squared, but you also want it to go through the point minus 2, 0. So when x is minus 2, y should be 0. And if you factor out the minus a, you see that a is equal to 0, or a is equal to minus 4. And minus 4, as suggested by somebody, Willem, as suggested by Willem, minus 4 is going to be right here. Very nice. So what was the question? Find the line through this point that is tangent to that. So the line occurs when a is minus 4. So let's answer the question. It's always a good idea to actually answer the question. Minus 8x minus 16 is the line tangent to that curve when a is minus 4. And it goes through the point minus 2, 0. Liam is asking where this comes from. So you have your tangent line here with slope 2a. that we found from the derivative, and it has to go through the point a squared. Somebody's asking, why can't we just find the derivative, plug it in as m, and then plug in to the point to find b? I believe that's what we did. I believe that's what we did, but you cannot leave the derivative as 2x, because if you plug in 2x here, then you get 2x squared, and that's not a line anymore. Remember, the derivative is a formula that gives you the slope of the tangent line at every point, but it's not allowed to vary as x varies, because then there would be no difference between your rule for the slope of the tangent line and x living on the line itself. Why do we introduce a in this question? We don't know, right? When we're looking for a line that is tangent to this, we don't know at what point it's tangent, right? It's unclear. It's not clear at what point we want to consider the tangent line for. So we give it a name, we call it A. Part B, determine values of the constant a and b, which will make the function continuous at -6. Everybody with us here? Right, you know what to do. We want to make sure our function is continuous at -6. What does that mean? So that, or such that, by a and b such that f of x is continuous at x equals -6. As the name suggests, the f is continuous if the limit as x goes to -6 from the left is the same as the limit as x goes to -6 from the right is the same as the function at -6. Right, so this is what we need. So let's evaluate these things. Limit as x goes to -6 from the left of your function. What is your function for values less than -6? Values less than -6, your function is square root of x plus 31. And what is that limit? right? You know this is well behaved. This is the square root of a polynomial. Everything's continuous. You can just plug in, and we get square root of 25, which is 5. What about limit as x goes to 6 from the right, negative 6 from the right? For values bigger than negative 6, for values bigger than negative 6, your function is a times x plus 5. Whose limit is, again, very easy polynomial. You can just plug in. And this is minus 6 plus 5 is minus 1. The limit is minus a. So for continuity, we need these two things to be equal. So a has to be minus 5. And we also need f of negative 6 which is a plus b. That also has to be equal to 5. But a is negative 5. So these two things coupled together mean that b has to be 10. So a is negative 5, b is 10. There we go. What last part, right? I mean, this is what we're using. Limit from the left has to be limit from the right, has to be the function at the point. So we found limit from the left, limit from the right. These have to be equal, so already a has to be negative 5. And then this last condition is this. So this has to be equal to that and that. So I'm just concentrating on the 5 part. If a is negative 5, then b has to be 10. Well, you have two equations, two unknowns there. You can use matrices to solve. How are we doing? Questions? People, I know you're not having any trouble finding this limit, right? We have two equations, two unknowns. Solve however you want to. Find k and l, which make the function differentiable at 1. Right? Can I rub this off? You know what to do. If your function is differentiable, it had to be continuous to begin with. If g is differentiable at 1, it had to be continuous to begin with. So let's make sure that it's continuous by looking at the limit as x goes to 1 from the left, making it equal to limit as x goes to 1 from the right, making it equal to g of 1. So let's see what happens here. For values less than 1, your function, for values less than 1, your function is kx squared plus l, whose limit is easily seen to be k plus l. And limit as x goes to 1 from the right for values bigger than 1, this is 6x minus 4, whose limit is easily seen to be 2. And g of 1, when x is 1, what is g of 1? You know what it is. It's k plus l. Right? This is the only place you're allowed to plug in 1 into this function. So for continuity, we need these 3 things to be equal. In other words, k plus l has to be 2. So you have one equation, 2 unknowns. We need another equation in order to solve. And that's where the differentiability comes in. Right? This is only continuity. But you know you need continuity as well. Right? Because if your function is differentiable, it had to be continuous to begin with. All right, so let's do the differentiability then. For differentiability, we want the derivative at 1 to exist. So this is, by definition, limit as h goes to 0 of g of 1 plus h minus g of 1 over h. So k plus l equals 2 makes it continuous, exactly. This makes it continuous. And now we want differentiability. We have just looked at g of 1. G of 1 was k plus l, which turned out to be 2. So this is g of 1 plus h minus 2 over h. And we want this limit to exist. So the limit as h goes to 0 from the left must be the same as the limit as h goes to 0 from the right. Let's work that out. Let's look at the limit as h goes to 0 from the right first. And what is that? This. When h is bigger than 0, this is bigger than 1. So we're plugging it into this. And this is 6 times 1 plus h minus 4 all over h. And this simplifies to 6h over h. Easily seen, right? Which is just 6. And if we look at the other side, limit as h goes to 0 from the left, for values less than 0, this is going to be less than 1. And so we're plugging it into this, which is k 1 plus h squared plus L minus 2 over h. Expand this. Let me rewrite this here. K plus L, K plus L. Expand, what do we get? This is k plus 2kh plus h squared k plus L minus 2. But k plus L is 2. So k plus L is 2, minus 2 is 0. These cancel out nicely. We can perhaps factor out an h from all of this. This was h goes to 0 from the left. We factor out an h. This is 2k plus hk over h. The h's cancel. As h goes to 0, this goes to 0, leaving us with a limit of 2k. So in order for the derivative to exist, in order for this limit to exist, we need 2k is equal to 6. Two equations, two unknowns. Where did the 4 come from? Right here. So two equations, two unknowns. I mean, it's easy to see that k is 3 here. And if k is 3, L has to be minus 1. And there it is, as Michael suggested. How are we doing here? Questions? Do we have time for one more? 4b, you are given that y is a function of t satisfying t cubed y plus ty cubed is equal to 2. Assuming y of 1 is 1, find y prime and y double prime of 1. Michael is asking the good question. Would we have to take the definition of the derivative, or can we just differentiate? Right? Because you might have noticed, I mean, I've rubbed it off now, but if you just differentiated both pieces and made them equal to each other at 1, then you would have gotten the same answer. So is this a shortcut? Does it always work? And the answer, it doesn't work. What you're doing there is forcing continuity of the derivative. And there's no theorem that tells us that the derivative has to be continuous. So that method doesn't work in general. Did we see a counterexample to that? I want to say we did, but thank you, Rachel. Right. So you have to use this. This is the way to do it. All right, let's tackle this one. And you know what to do, right? I mean, this is a very simple implicit differentiation question. So we're told that this defines y as a function of t. So differentiate the whole equation with respect to t, assuming y is a function of t. So if we differentiate, what do we get? Both of these are products, so product rule applies. Differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one. Well, let me call it y prime. And same thing with the second term, product, so differentiate t, leaving y cubed fixed, plus leave the first one fixed, differentiate the second one. Second one is something cubed. So this is 3y squared times the derivative of the inside times y prime, derivative of two is 0. You know what to do. Bring everything, leave all the y primes on one side, bring everything else to the other. Can we do that in one step in our heads? Factor out and divide, right? we get a minus 3t squared y minus y cubed all over t cubed plus 3ty squared. Is everybody with us? All right, and let's plug in t equals 1. When t equals 1, y is equal to 1. So plug in 1, 1. What do we get? This is minus 3 minus 1 is minus 4 over 4. In other words, minus 1. Yeah, that's what we're doing, right? We're plugging in 1 for t and 1 for y. I mean, be careful, right? The 1 is not, y equals 1 is not arbitrary, right? I mean, it's given. It's not the same as t. It's its own specific value. All right, and now from here, I mean, we also want the second derivative, right? Sorry, Rachel, where did I lose you? All we're doing is plugging in t equals 1 and y equals 1. Right? I mean, it's given. When t is 1, y is 1. So we're just plugging in t equals 1 and y equals 1. We did not make this up here. This y equals 1 is not our construction. It's given in the question. When t is 1, y is 1. This could have been different. It could have been a 4 or anything else. It's given in the question. We were also asking for the second derivative, so differentiate this whole equation with respect to t. Left-hand side becomes y double prime. And here, you've got a quotient. So quotient rule applies. V u prime, the derivative of this, which is, here you've got a product, so product rule applies. 6, so minus 6ty minus 3t squared y prime minus 3y squared y prime. So vu prime minus u, so let me change that to a plus by factoring out a negative. So minus u v prime, the derivative of the denominator, 3t squared. Here this is a product, so product rule applies. Derivative of y squared is 2y times the derivative of the inside. The whole thing is over this squared. Let's finish that up by plugging in. When t is 1, y is 1, and y prime is negative 1. Right? Because now you have an expression involving t's, y's, and y prime. So this is going to be 4 minus 6 plus 3 plus 3. So that is 0. That is again 4. This is 3. Plus 3 is 6. This is minus 1. And so you get another 0 there, is that right? The whole thing over 4 squared. Is it 0? I think it's 0. Thank you, Michael. Sean, no? Have I made a mistake? Shouldn't it be 1? It could be 1. What have we done? T is 1, y is 1. So this is 6, but y prime is negative 1. And this is 1 and 1. So this is 6 minus 6. That's gone. And here, what's happening? This is minus 6. This is plus 3. And this is again plus 3. I think it's 0. I think it's 0. 0 sounds good. There it is. How are we doing? Questions here? Is everybody with us? Right, I mean, we found y prime in the previous step, and now we're just replacing. Try it over the weekend. Let me know if a mistake has been made. And we'll pick this up again on Monday. Thank you all for coming. You guys have a good weekend. And I'll see you next week.